Okay, so right here is where section 10.3 begins. I've kind of combined section 10.2 and 10.3 just because I feel like the counting techniques that we're using are very similar to each other. Okay, so keep that in mind that 10.2 and 10.3 are kind of combined here. There's a definition. It says the number of permutations of n different objects taken r at a time, denoted by, the way that we read that is n permute r, as n permute r is the number of ways to arrange r objects taken from the n objects if two things happen. If, number one, if no object is repeated, and number two, order is important. Okay, so just to give you an example of order mattering, suppose that you were going to go to get some money at an ATM. Okay, and you put in the debit card. And let's say your PIN is 5401. Okay, but instead of entering in 5401, you enter in 1045. Are you going to get your money? No, because the PIN was not correct, right? So that would be an example of a situation where you'd have a permutation, okay, because order matters. Okay, now the other thing about a permutation is no object is repeated. Okay, so that's important. Here's the formula that we use for permutations. N permute r is n factorial divided by n minus r, the quantity factorial. Okay. Now, also in section 10.3, we look at combinations. Okay, and it says the number of combinations of n different objects taken r at a time, denoted by NCR. The way that we read that is n choose r, is the number of ways to arrange the r objects taken from the n objects if, again, no object is repeated, but this time order is not important. Okay, so order matters with a permutation, order does not matter with a combination. In both the permutation and combination, no object is repeated. Okay, so as an example, suppose that you're at the grocery store and you're in the cereal aisle. Okay, and suppose that the three cereals that you select to purchase are going to be Kix, Cheerios, and Apple Jacks. Okay, now if you walk up to the checkout, and instead of laying it down like Kix, Cheerios, and Apple Jacks, you set it down as Apple Jacks, Cheerios, Kix. Is that going to matter? No, it's not. Okay, it's not going to matter what order you put these in. The same transaction is going to be made regardless of what order you place these in. Okay, so that would be an example of a combination. NCR is very similar to NPR. The only difference is that you're multiplying the denominator by r factorial. Okay, so n factorial divided by r factorial times the quantity n minus r factorial. Problem 13 is an example where I want you to compute 5 permute 3 and 5 choose 3 using the formulas that are above, and then check your answers using a calculator. Okay, so 5 permute 3, n is 5 and r is 3. By the way, n is always going to be the bigger number. Okay, so the bigger number is always going to go on the left. Okay, otherwise, it wouldn't make any sense if you were to write 3 permute 5. Since you've got 3 objects, you can't select 5 from the 3. Okay, so I'm selecting 3 objects from the 5 objects. Okay, so n is 5, r is 3. If I use the formula here, 5 factorial divided by 5 minus 3 factorial, 5 minus 3 is 2. Okay, so 5 factorial divided by 2 factorial. 5 factorial, by definition, would be 5 times 4 times 3 times 2 times 1. 2 factorial is 2 times 1. So 2 times 1 is going to cancel with 2 times 1 in the denominator, leaving me with 5 times 4 times 3, which would be 60. Okay, so there's 60 different ways that you can select 3 objects from the 5 objects if order is important. Okay, now what if order does not matter? Okay, what if Kix, Cheerios, and Apple Jacks is the same thing as Apple Jacks, Cheerios, and Kix? So you don't have to count that as two different things. Okay, you only count that as one. So what if I want to compute 5 choose 3? Okay, n is 5, r is 3, so 5 factorial divided by 3 factorial times 5 minus 3 factorial. 5 factorial, that's the same as 5 times 4 times 3 times 2 times 1. 3 factorial, that's the same as 3 times 2 times 1 times 2 factorial, that's the same as 2 times 1. Also note, 3 factorial times 2 factorial is not equal to 6 factorial. Okay, 6 factorial we've already done earlier, that's 720. Okay, I'm not going to get 720 by multiplying 3 times 2 times 2. Okay, so let's see, the 3's are going to cancel, the 2's are going to cancel, the 1's are going to cancel. And that leaves me with 5 times 4, which is 20, divided by 2 is 10. Okay, so if I have 5 objects in front of me, and I'm going to select 3 objects from the 5 where I don't care about the order, there are 10 different ways that I can make my selection. Okay, by the way, whenever the numbers are the same for a combination, it will always be much less than that of a permutation, because with a permutation, order matters. Okay, with a combination, order does not matter. Identifying whether we have a permutation or a combination is very important. Okay, so in problem 14, I want us to decide whether each item is a permutation or a combination. Okay, the big thing here is to see if order matters or if order does not matter. Okay, so what if we have a telephone number? Well, order is going to matter, right? The order of the digits, so that's going to be an example of a permutation. Same thing with the Social Security number. If you take your Social Security number and you mix up the digits, it's not going to be the same Social Security number because order matters. Okay, so that'd be a permutation. What if you have a hand of cards in poker? Well, that's going to be a combination. If you have 5 cards in your hand and you mix up the 5 cards, you're still playing the same hand, right? You're still playing the same group of 5, regardless of what order the cards are in. A committee of politicians. Okay, so if John, Rick, and Steve are the 3 members in the committee, that's the same thing as Steve, Rick, and John being the 3 members, right? So that'd be a combination. Now, if in the problem we were told that we were electing like a president, a vice president, and a secretary, for example, then now that's different because John being the president is not the same thing as John being the secretary. Okay, so that would be an example of a permutation there if you're electing positions. But they didn't say anything about electing positions there. Part E, the combination on a combination lock. Okay, so let's suppose that you have a lock with 30 numbers on it, and to open the lock, the code is 17423. Okay, now if you go 23-4-17, you're not going to open the lock. Okay, because order matters. That'd be a permutation. Part F is where we have a lottery choice of 6 numbers where order does not matter. Okay, so they're telling us order does not matter. That's a combination. And a license plate, that'd be an example of a permutation. So if you take your license plate and you mix up all the digits that are there, you're not going to have the same code there. Order matters. Okay, so let's look at problem 15 here. An automated teller machine, an ATM, requires a 4-digit personal identification number, which is a PIN, using the digits 0 through 9. The first digit may be a 0. How many such PINs have no repeated digits? Okay, so a PIN number on a debit card, that was one of my earlier examples, and I said that was an example of permutation. Okay, so I would use a permutation. There's 10 digits total, if I can select 0, right? So 0 through 9, there'll be 10 digits, and I'm going to select 4 digits from the 10. Okay, so I'm selecting a 4-digit personal identification number. So 10 permute 4 is what I have to compute. Okay, I'm going to compute some of these earlier ones by hand, and then I'll show you how to do that in the calculator. Okay, So 10 permute 4, n is 10, r is 4. Okay, so I got 10 factorial divided by 10 minus 4 is 6 factorial. 6 factorial is 6 times 5 times 4 times 3 times 2 times 1. Okay, so I'm going to cancel these 6 numbers with part of the 10 numbers that would be in the numerator. That way in the numerator, I'm going to be left with 10 times 9 times 8 times 7. Okay, 10 times 9 times 8 times 7 is 5,040. Okay, so there's 5,040 such pins that are available. Okay, now there's a key thing here that can very easily be overlooked. How many such pins have no repeated digits? The no repeated digits is important. Okay, because with a permutation, remember, or a combination, no object is repeated. Okay, so anytime there's repetition going on in the problem, it will not be a permutation or a combination. Anytime there is repetition, it will be, or it has the possibility of being a permutation or combination. Okay. Now, with a permutation, you can always answer the problem by using the fundamental counting principle instead. Okay, so if I have, if I'm going to create a 4-digit number, well, there's no repetition. That is important. Okay, with 0 through 9, I'm just going to select one digit there. So I got 10 possibilities. So 10. Okay, now once I select a digit, since I can't repeat digits, there's 9 digits that remain. So I'm going to select one of the 9. Okay, and then 8 digits remain. Okay, select one of the 8, and then finally 7 digits remain. Select one of the 7. So now 10 times 9 times 8 times 7, that's 5,040. Okay. Now here's something to know. The fundamental counting principle and permutations are kind of intertwined. Okay. It is not true with the fundamental counting principle and combinations. Okay, when the problem requires a combination, you cannot use the fundamental counting principle. Okay, and I'll talk about that a little bit when I get there. Okay. By the way, if I go to the calculator and type this in, okay, turn the calculator on, what if I hit 10 and then math, okay, and then go over to PRB. Oops. So option 2 is where I've got a permutation, and option 3 is where I've got a combination. Okay, so I got 10 permute 3, and hit enter. That's 720. Oh, whoops, 10 permute 4. Sorry. Math option. Okay, 10 permute 4. That's 5,040. Okay, which is what I was getting there. Problem 16, how many ways can a president, vice president, and secretary be determined in a club with 12 members? Okay, so if Steve, Rick, and Peter are the 3 members that are going to be elected president, vice president, and secretary, Steve being the president is not the same thing as Steve being the secretary. Okay, so if you move the people around, then they're going to have different positions, and that's going to matter. Okay, so the thing that we need to think about here is that this is an example of a permutation. Okay, and I got 12 members. I'm going to select 3 of them to be the president, vice president, and secretary. So I need to find 12 permute 3. Okay, n is 12, r is 3. So 12 factorial divided by 9 factorial. Now these 9 numbers can be canceled with part of the 12 numbers in the numerator. Okay, so in the numerator, I'm going to be left with 12 times 11 times 10. 12 times 11 times 10 should be 1,320. Okay, so there's 1,320 different ways that I can select a president, vice president, and secretary from this club. Again, I could have, if I wanted to, use the fundamental counting principle. Okay, so once somebody is president, that same person can be president again. Okay, so that there's 11 people left for the vice president position. Select one of them. Okay, and then 10 people would be left for the secretary position. Select one secretary. Okay, again, the fundamental counting principle and permutations are always, you know, related there. Okay, so you can answer one or the other. Okay, let's try problem 17, where it says Tom wants to buy 10 different books but can only afford 4 of them. In how many ways can he make his selection? Okay, so let's suppose that the 4 books that Tom selects are astronomy, physics, psychology, and math 110. He's got to select that book, right? Well, if I mix up those 4 books, that's not going to matter, right? He's still going to purchase the same 4 regardless of what order I said those in. Okay, so that would be an example of a combination. Okay, there's 10 different books. He's choosing 4 of them to purchase. So n is 10, r is 4. Okay, and I need to compute 10 factorial divided by 4 factorial times the quantity 10 minus 4 factorial, or 6 factorial. Okay, now these 10 numbers, well, 6 of them can be canceled there. So 6 times 5 times 4 times 3 times 2 times 1 can cancel with the 6 times 5 times 4 times 3 times 2 times 1 in the numerator. So in the numerator, I'm going to be left with 10 times 9 times 8 times 7. And in the denominator, I still got this 4 factorial. 4 times 3 times 2 times 1. And I guess I can do some more canceling here. So 4 times 2 is 8. Those are gone. 9 over 3 is 3. Okay, so I'm going to be left with 10 times 3, which is 30, times 7, which is 210. Okay, so there's 210 different ways that Tom can select these 4 books. Okay, now something very important to say is that unlike with a permutation, how you can always use the fundamental counting principle instead of using a permutation, that will always happen, okay, that will never happen when you have a combination. Okay, so when the problem requires a combination, it can only be done using a combination. Okay, if I were to compute 10 choose 4, okay, here's 10, math, got number 3, 10 choose 4, gives me 210. Okay, notice how that number is much lower than 10 permute 4. Okay, that always happens. Okay, so let's go ahead and stop right there in the notes.